All right, so today we are going to look at, or we are going to conclude on that session where we're discussing the model evaluation and how the numbers in the should be interpreted so as to inform us to make that decision as to which model is giving us a better performance beyond the accuracy. And I did say that when it comes to model evaluation, the way we do or the way we evaluate models in classification is different from the way we evaluate models in regression or any other machine learning technique. And the example I cited the last time was you have footballers all playing in the same sports, but then the manner in which we evaluate the performance of a goalkeeper is definitely going to be different from the manner in which we evaluate the performance of a striker or a midfielder or any other person. So over here, we are seeing that when we talk about model evaluation, and we are being specific over here to classification. So model classification evaluation involves assessing how well a classification model predicts labels by comparing its prediction to true labels. So it is the predicted ones that we are comparing to the true labels or the actual labels so that we can make that informed decision. Now, every predicted instance will belong to one of the following categories. So if it is classification, it is either going to be a case of, okay, you predicted it was right or you predicted it was wrong. But then those categories could be broken down into two for each. So, they become four. And the first one you have over here is the true negative. So the model predicts a negative class. So in this case, the model predicts a negative class. So there's an example, okay? It predicts a player will miss a penalty like the example I cited last week. And indeed, the player misses the penalty. So this is a true negative. It was true for the prediction and it was in a class of negative because the person missed. We can look at other examples where maybe it is, if it is a disease classification model that you built, then a true negative is going to be a predicted true for the person not having the disease. And indeed, the actual thing says the person does not have the disease. So it is a true negative. Now, in the case of true positive, the model incorrectly predicts a positive. Now, a typical example is predict a player will score, but the player misses. So this one is very clear. It is a false positive. It predicted that the player will score, but then the player missed. So it predicted a positive, but then it was false at the end of the day. That's basically what this means. And then we have the false negative. This is when the model incorrectly predicts a negative class. So predicts the player will miss, but the player scores. Okay, there's a typo over here. It predicts the player will miss, but then the player scores. So this is a false negative because if I predict for you to miss, that means I'm putting you in the negative class. But the question is, am I being truthful or for some reason?
Hello, Mr. Bernie.
Yes, please.
Oh, sorry, please. I think you're not able to see your screen.
Oh, really? Oh, sorry.
Um,
Okay. So this is my screen. Oh, sorry about that. Okay, so these are the things I'm reading from. Okay. So the first one we had over here was the classification evaluation involves assessing how well a classification model predicts labels by comparing its predictions with the true labels. And these were the examples I was citing. So in the case of this one, which is a true positive, the model correctly predicts into a positive class. So over here, the example is predicts a player will score, and indeed, the player scores. So the prediction was into a positive class, and the actual was actually the player scoring. Now, these categories that we are dealing with forms a basis for confusion matrix, which is essential for evaluating the performance of a classification model. So I believe in order to understand this very well, once we bring in the confusion matrix and we see those true positive, true negative, and all that, we're able to make sense out of where the numbers are coming from and how we interpret them. Now, once we have those true positive, true negatives and all that, we can get a precision. Now, this is a ratio of correctly predicted positive observations to the total predicted positive observation. And we spoke about this last week. So the formula for precision is the true positive divided by the true positive plus the false positive. So over here, we are looking at how accurate or how precise we were. So everything you see or all the parameters you see in the formula are basically the more positive ones. So these are the explanations we have over here. Now, in the case of recall, this is more or less the reverse, trying to look at what if it wasn't too correct? How bad did you do? So over here, it measures the ability to identify all actual positives. So over here, the recall is going to be the true positive divided by the true positive plus the false negatives. You realize that in this one, we are looking at the false positive for the precision. For recall, we are considering some false negative predictions that were made in there, because at the end of the day, if there are some false negatives, they are going to affect the model's performance. And then we come to the F1 score, which we are saying that the F1 score is a harmonic mean. So today we're actually going to spend time to do some of the calculations manually by hand and compare it with what a typical model will be giving us and see how things goes. And then we have the support. So now you could remember that in the classification report, which you are going to see one very soon, there's always some support metric that shows. And this is the number of actual occurrences of each class in the data set that was used in the evaluation. And then we have the accuracy. So the overall proportion of accurate predictions. So the accuracy is going to be equal to the correct predictions over the total predictions. And then there is the macro average and also the weighted average. And we see that in the classification reports, and we are going to analyze, because some models will give you very good accuracy, recall, but then when you check the macro average, it should also tell you why you should be very careful in banking all your hopes in on such models. So the macro average is the average of metrics across all classes, treating all classes equally. So over here, the macro average, you look at the metric 1 plus metric 2 plus metric 3 all the way to metric n, if they are, let's say, different metrics, all divided by the total number of classes. So in the case of these ones, and the reason why we are using, for instance, metric 1, metric 2 is the metric 1 can be the precision, metric 2 can be F1 score, metric 3 can be recall, and all those things, all divided by the total number of classes that we have. Now, it is also important to know that if we have all these things we are saying, for instance, with the penalty missing or not missing, these are all binary classification. But then when we have the example we cited with the Iris setosa, and at least we have 3 classes for the flowers or the species of the flowers. We have Iris virginica, Iris setosa, and Iris versicolor. So we can have a true positive with regards to Iris setosa with respect to the other 2 classes. Okay, and that's why those confusion metrics, we have 3 rows and 3 columns. All right, so the macro average tries to sum everything up, but then there's a weighted average. And now the weighted average, average of metrics weighted by the number of samples in each class. So this one is weighting things. And if you look at the formula very well, it is the support one, the number of instances that were used in the prediction. And that's why I told you last week that sometimes, depending on the number of instances, because a lot of the times, the splitting is done randomly. So you may have a situation where maybe you have 3 classes, but then, and maybe among all 3 classes, like the Iris setosa and stuff like that, maybe together, maybe 100 instances were used. Now, if you are to divide 100 by 3, definitely we are not going to have an equitable distribution. Even if it is 30, 30, 30, we'll still be left with 10. Where did it go? Definitely some classes will have more instances than others. And this is where we are saying that, okay, the support is definitely going to be the total number of instances, okay? The total number of occurrences, okay, or instances from the data set. So when we are dealing with the weighted average, we are looking at the supported number of instances that were reserved randomly or out of that random distribution, multiplied by that particular metric plus the support 2 for maybe the second class, multiplied by that particular metric for that class, then we move all the way, all divided by everything together. So definitely support 1 plus support 2 plus is definitely going to be the total number of n. And like I said, we are going to do some manual calculations by hand to actually check this. So now let's say for the 10 penalties, we are saying that 5 goals predicted and 4 were actually scored. What it means is our true positive, because we predicted 5 goals, so that means our true positive is 4. These were the actual ones that actually happened. And our false positive is 1 out of this particular set. Because at the end of the day, it's almost as if the support is a 5 goals. That's the total number of occurrences. And we predicted that all 5 were going to score. However, it was only 4 that were scored. So those were the true positive. And now the false positive, we predicted to a positive class, but then it was false. So that's going to be the one left over there, which actually means that this one was actually missed, but then our prediction got it wrong. Now, we also have an instance where we have 5 misses, okay, or 5 misses predictions. So we predicted that, oh, out of these 5 penalties, the person is going to miss 5. And then indeed, 3 of them were missed. So that's going to be the true negative, because missing a penalty, we are considering it as a negative class. And then out of the 5, 3 were missed. So yes, those were the true negative. But then false negative will account for 2 because these ones were actually scored realistically. So now over here, before we even write the code to actually assess everything we've done so far and also do the manual calculation by hand, we are saying that for the accuracy, it is the overall fraction of correctly classified instances. So for accuracy, we are looking at how correct we were. And sometimes it may skew our understanding of how good, quote unquote, a model is performing, because the goodness of a model is not just the accuracy, but then how it is also able to get things wrong if it is supposed to be wrong. Now, in the case of the macro average, a summary over here is the arithmetic mean of the precision, the recall, and the F1 score. Over here, you could see that I was using metric 1, metric 2, and I did indicated that there were those matrices, the F1 score and all those things, the recall. Those were the things we were putting together as these ones. And over here, we are treating all classes equally. We are treating all classes equally. However, you realize that in the case of the few examples that we've cited, you realize that the support for some of the classes will differ, and for which reason we may have one class having a lot of support and another not having a lot of support. If you are going by the macro average, we are not going to make a good judgment. But then when we come to the weighted average, then this one is looking at the averages weighted by the number of true instances or the number of support it had. Now, in order to make our work very easy for us, okay, because if we are to build a classification model and go through that process, that's going to take about maybe 20 minutes of our time. So quickly, we are just going to fast track the process and actually go straight into doing some analysis of performance based on some values we are going to give our model. So we are going to run some few imports. So I'm going to say from sklearn.metrics, I want to import classification reports and also get the confusion metrics and let's say accuracy score. And let's run this and let's wait. Okay, so let me do another import numpy as np and import pandas as pd. So let's get these matrices or these libraries out of the way so that we can actually do some few things. Now, what I want us to do in terms of doing the analysis over here, like I said, we should have built a model to do all those things. We already have models that we are comfortable with. So let's quickly look at these ones exclusively. So let me try and use this one to get some few things going. So if you are to have and let's say, okay, let me just use this one so that it makes a lot of sense. Okay, so we have some round, okay. And then let's use this one to represent, okay. Let me use a different color. Let's say black. So clearly you can see two classes over here. And let me erase this one. Good. So let's assume the round ones are the ones for, let's say, the positive class, okay, and the black ones are the ones for the negative class. So to have this shows that maybe you scored a penalty, and to have this shows that you missed the penalty. So clearly, we can see that there were three scoring over here, and then 2 misses. But then this is maybe what we have with the actual data sets, okay? And now we move to an instance where our model has made some predictions. So it is out of the predictions from our models that we can actually make a judgment based on whether it did well or it didn't do well. So let me have this. And in here, let's assume, so this is the actual, okay? And this is the predicted. So inside of the predicted, if we end up having 1, 2, 3, okay, and then for some reason we had 4 over here before we had 1 black. So let me bring in the black over here to balance things up. Good. So our work is cut out for us. So clearly you can see that this was the actual data set, which had scoring 3 and missing 2. But then our model did a prediction and came up with scoring 4 and missing 1. So clearly we can analyze this and try and figure out, okay, what is in terms of the true positive, the true negative, and all those things over here. So over here, it told us that it was going to score a scored. So these ones have been cancelled out. It told us we were going to score a scored. Now it told us we were going to score a scored, but then this one, it said it was going to score, and then it missed. So over here, if we had to draw our own confusion matrix, which we are going to draw very soon, but then let's just try and get a caricature of it over here. We know that this side is going to be the true positive, okay? So the true positive over here was, we're going to score, we're expecting 3, but then we scored, we overscored. So let's concentrate on the true negative, the false positives, okay? So the false positive, this one was a false positive with respect to the actual data set that we have over here. Because the actual data set says that this one is supposed to be a miss, but then it was predicted as positive. So over here, we're going to say that we're going to have a false positive of 1. Okay. Now, when we come to do you have an instance where, okay, so this one was correct. So this one was a true negative. So with a true negative, we are going to have 1 over here. This is going to be true negative. And then in the case of the true positive, we all have these 3 over here. So we are going to have 3 over here. And in the case of the, this one is going to be false negative. So false negative false negative. We were supposed to predict negative, but then we predicted good. So no, this one is going to be 0 because we don't have any instance of such, because we were supposed to predict false and it ended up predicting true, kind of. So we don't have any instance of that over here. So at the end of the day, if we sum everything up, we are getting 5, okay, because 3 plus this is giving us 5, and those are the number of things we see over here. So we have 4 plus 1, so everything over here, the numbers we see over here, should sum up to the number of instances that we use for our model evaluation. So what we are going to do is we are actually going to model this kind of a thing, okay, inside of our code. So now that we have NumPy, remember, let's assume every 0 we see over here is, let's say, a 1, okay, and the black is supposed to be the 0. So if I'm to do this correctly, based on what we have over here, okay, I just want us to have the visualization. I can see that, let's see, this is the actual and this is the predicted. So now let's model the actual data. So I can see actual underscore data is going to be equal to, if I'm to do np dots, and for the purpose of this, let me do np dot once. And how many instances of ones that we want? We just want 5 for now, okay? Remember, what we are trying to come up with is these ones are the ones, and these ones, the black ones, are going to be the zeros, okay? So let's just do this for now, and we are going to change some few things. So now when I do this and run this, and if I'm to do a preview of the actual data, we are getting 1, 1, 1, 1, 1 over here. Okay, now we know that this is 1, 1, 1, and the last two should be 0. So that if the last two is 0, I can do some slicing technique over here and put the last two to 0. So I can see that from, I can see that from the index starting from -2 till the last one, I want to assign 0 to it. I don't know if that makes sense, okay? So when I run this, everything looks good. And now when I come and do a preview of the actual data, I'm getting 1, 1, 1, 0, 0, like I have over here, based on the our own definition of the variables and also the shapes that we are using over here. Please, I hope you're on the same page. Okay, so I mean, I presume silence means consent. So let's just work with this. So we are saying that the zeros are representing 1. That means the person scored the goal, okay? And the blacks we have over here are representing 0. So in this true instance, we are getting a 0, we are getting a 1, 1, 1, then 0, 0. And that's exactly what we have over here, 1, 1, 1, and then 0, 0. So that's the actual data. Now let's look at the predicted data. So let's look at predicted underscore data. And this one is for starters, let's do np dot once, and later we are just going to change the last one to a 0. So I'll put in 5 over here. I'll run this. I'll do a control C, control V, and then what I want is get the last, okay, the last index, and assign this to a 0. So when I run this and now come and do this over here, we have this showing up over here. So this one is a 1, 1, 1, 1. That's the predicted 1, 1, 1, 1. And the last one is 0. And let's assume these are the things we got from our model. And we now want to build a classification report and do things and see how things go. First of all, let's build a confusion matrix and see if it is actually a resemblance of what we have manually done over here based on what we have. So to get a confusion matrix, of course, we have called this over here. So now let's build this confusion matrix. And now all that we need to do is to pass in the actual data and the predicted data. All right. So let me pass in this one first. I think any one of them could go. The most important thing is you have both of them in there. So actual data, and then we pass in the predicted data. And then, okay, things have flipped a little bit. Let me just do the actual first before the predicted. I want things to look, okay, go with the other one. So the predicted versus the actual. Okay, so in terms of what we see over here, just that the meanings of whatever thing we have over here has flipped. Is that okay? But the main thing is, for instance, this is supposed to be the true positive, okay, which is showing us 1 over here, and the true negatives. I don't know, but then if you can look at this very well, okay, it is the same thing we see over here, one way or the other. Okay, it's the same thing we see over here, one way or the other. Now, what I want to do is what I want to do here is I'd want us to actually do a plotting of this to make this work very well. So let me import Seaborn as SNS. And now if I'm to do SNS dot the heat, let me save this in the variable called M so that we can bring this one over here. So heat map and then pass in M over here. Okay. And let me bring in the annotation. So and not is equal to true. All right. So based on this, what we have. So I think when the how do you call it? When the labels came in here, that's why things are now beginning to make sense, because the numbering has changed. So over you can see that zero, the class 0 is showing up over, but over here we are looking at the class 1. Okay, that's why things have flipped a little bit, because here you have the class 1 showing up as the number of instances we have over here that was correctly predicted was 3, and the ones that were wrongly predicted showing over here as 1, but then was wrongly predicted to be 0, showing up as 1 over here. And now in the case of 0, which was actually 0, based on the data that we have over here, the blacks are 0, okay? So this was 0, and it was actually 0. Based on the prediction, it was just 1 over here. And instances where it was 0, but then predicted as 1, there was none. So that one was 0. So that's why I said it has flipped a little bit, but at least with the labels that we see over here with regards to the class labels, we could see that it is the same thing, just that things have flipped a little bit. All right. So now that we have this, let me just put matplotlib.pyplot as PLT. So let me just import matplotlib.pyplot matplotlib. Okay. All right. So plt.show, just to take care of whatever thing we have over here. All right. So these are confusion metrics. And now what you are seeing now, okay, now that we have this thing showing up, we want to now start calculating, for instance, all the things we've seen over here, okay, which has to do with the precision. And we are seeing that the precision is going to be equal to the true positives, everything in the true positives. In this case, please remember it is 3 over here, okay? Like I said, things have flipped a little bit over here. That's why, you know, the reason why things have flipped is because Python indexing starts counting from 0. That's why the 0 will come before the 1. But in our case, we had looked at things in the opposite direction. So over here, we are seeing that in order to calculate for precision, we are going to have the true positives all divided by the false positives plus the false negatives. So if I'm to do this calculation by hand over here, and let me just bring in my calculator. Based on what we know, okay, let me put this over here. Based on what we know, it is going to be this 3, okay? I believe so, yes. It's going to be this 3 divided by the 3 plus false positive 1. So let's say 3 divided by 4 at the end of the day. So 3 divided by 4. And I'm getting a 0.75. So based on the calculations, the manual calculations that we've done over here from our confusion metrics, we are expecting a precision of a 0.5. So now let me just write that one over here. So I'm going to say the precision based on our calculation is going to be a 0. Is it 75 or yeah, 0.75. Now let's do the calculation for the other ones. The calculation for, let's say, recall. Recall is going to be the true positive divided by the true positive plus the false negative. So you know that this is the true positive, that's 3. Okay, so it's going to be 3 divided by the true positive again plus the false negative. The false negative over here is 0. So clearly we are going to get a 3 divided by a 3. Good. So we are getting a 3 divided by a 3 because this is false positive, which is 3 plus 0. So 3 divided by 3, we are getting 100% over here. So over here, our recall is going to be 100%. All right. Now let's move on to the other calculations. And we can look at the F1 score. So the F1 score is a harmonic mean. So we have our recall and we have our precision. So we can add these two. So 1 plus, so the denominator is going to be a 1.75 because that's going to be the precision, which is 0.75 plus the recall, which is 1. So that's 1.75. And then we multiply that and everything. So let's do it. So let's do the multiplication first. So we do a 1 multiplying a 0.75. Okay. Oh, why did I even do this in the first place? So that's going to be a 0.75, okay, times 2. So 0.75 multiplied by 2 divided by a 1.75. So divided by a 1.75. And that's giving us a 0.85. That's the harmonic mean. So, or approximately 0.86. So let's put the approximation over there. So the F1 score, is approximately a 0.86. Okay. So things are beginning to look good over here. Now let's look at the other ones. Well, with the macro average and other things, we are going to see them later. So when we do a manual calculation, this is what we are getting. Let's see what classification report gives us if we are to use scikit-learn and maybe do a comparison and see whether we were right or wrong. Okay. So let me bring in the classification report. So I can do a Control-C over here. And then all that I need is indeed everything I have over here. So the predicted data and the actual data. Now, let me put this in a variable called reports. And now let me do a printing of this report and see how it goes. Okay, so now let's do a comparison of this. And we are seeing, okay, things are flipping over here. Well, once again, based on the way things have changed in the original, how do you call it? In the original structure as you see it over here. But then we get a sense of how things are, at least with the F1 score, it was going to be it. It is just the precision and the recall that has flipped and also has changed. So over here, we are seeing that we are getting the approximated value of a 0.86 over here. That's exactly what we have showing up over here. Good. Now, you are also seeing that with the values we had over here, and because of the flipping, precision is now taking the place of recall and stuff like that. So let me just do it this way so that it conforms to what we have in here. So we are seeing a precision of 100%, okay? And that's what we see over here for this particular one class, okay? And then we are seeing a recall of a 0.75. That's what we are seeing over here. And then the harmonic mean between these two is this 0.68. And then the support is 4. The support is 4 because based on what we see over here, you see that for the one class, remember we are representing the zeros with 1. We had 1, 2, 3, 4. Those were the ones we used in terms of our prediction. Is that okay? Good. Now, in the case of what we have over here for the zero class, our precision was a 0.5. Our recall, remember, recall is trying to predict how wrong we were. And the question is, was there any predicted value that was wrong with respect to 0? The answer is no. So over here, the recall, and that's simply because of the support that we have, because we just had 1. And that 1, in terms of its prediction, was correct. But then the other 1 made it flip a little bit. That's why we are getting a 0.5 over here. Good. Now, what we see in here, when it comes to the overall accuracy, we are getting an 80% accuracy score over here. So maybe this one looks good. But then if we interrogate this further, then looking at just the support alone, we need to be very careful. Maybe we can test or evaluate this model with different instances of our data sets. Maybe for some reason we have a new data set that's having the same features as the old one we used in building the model. We can use that new data set to test so that the splitting is a little bit measured in terms of what we are using to evaluate the model and also what we are using to compare. Good. Now, what you see over here is the macro average. And clearly you can see that for the macro average, for the precision, we are getting a 0.75, 75% over here. Now, let's go back to the definition or the working definition we have over here with the macro average. And over here, all that we are doing, especially with this formula, is that the macro average is the metric 1. For instance, the recall plus the precision plus the F1 score, all divided by n, the number of classes. So over here, we know that the number of classes we have is 2. So now let's do that manual calculation and see. We can see that these are the matrices. Is that okay? So for the matrices, we have, for instance, 1 plus this, that's going to be a 1.75. So 1.75 plus this one, a 0.86, 0.86. So together we are getting a 2 point, whatever, okay, a 2.61. And the number of classes we have over here is 2. So, oh no, I think, no. It's supposed to be column wise, okay? So over here is going to be a 1.15, sorry, 1.5 divided by 2. Okay, so it's going to be the precision for the class 1 and the class 2, okay? If there are about 10 classes, we do the precision of all those classes divided by the total number of classes that we have. So it's going to be 1.5 divided by 2, and that's why we are getting the 0.75 over here. That's with the macro average, and the same applies over here. So this is going to be a 1.75 divided by 2. So a 1.75 divided by 2. And that's what we are getting as, approximately 0.88. So those are the values we have. And over here, the F1 score is also what you see over here. But then it is important to know that when we just do things like this, then we are saying that it does not take into account the imbalances we have in our data sets. Because over here, it is very clear that there's a big imbalance over here if we just look at the supports. Because for the first class, there was just only 1 that we are using to test. And even with that one, the precision is not that good. So it becomes very difficult for us to evaluate properly what has actually happened for our model to even make good predictions. But of course, no model has been built yet, but then we are just using based on the values that we have to make that judgment call. Good. So if we are to properly analyze this, then our best way of evaluating this holistically is to look at the weighted average. So with the weighted average, the formula that we are most interested in is the support 1. That means we are weighting things over here. Multiply by the matrix 1 plus support 2, multiply by. So this one looks good. So now let's see. So over here is going to be support 1, okay? Is it all over support 1 plus support 2 plus support 3? Okay. So it is going to be support 1. So 1 times this plus 4 times this. So 1 times this is 0.5 still, and 4 times this is going to be 4. So we are getting a 4.5 from this, all divided by 5. So we are going to get a 4.5, I believe, all divided by 5. And we are getting a 0.9. And that's exactly what we get for the weighted average over here. Okay, that's a 0.9 for the weighted average we see over here. So at least clearly you can see that these calculations, they are not magic. They are based on, I mean, real formulas, and the calculations are done for you. Except that if you are using scikit-learn, you have the benefit of having these things just done for you in a blink of an eye, okay, very quickly and very swiftly. But then our issue as engineers is to understand these numbers, what they mean, and how we can interpret our results accurately. Because this may look very very small, but then some of these models are going to be used for medical applications, okay? And if the example Dr. Mills always give is, if let's say there's a disease diagnosis system for breast cancer, and part of the medication we know for breast cancer is chemotherapy, radiation, and maybe sometimes I don't know the right medical word, but then they do amputation of maybe the affected part. So if it is somebody like I know so much, no, not I know so much, but then I like his music, Bob Marley. Bob Marley had a foot cancer, and that foot cancer was spreading. Imagine there was a misdiagnosis that, oh, this is not cancer, or this is cancer, and you go and chop off his foot. Meanwhile, it turns out that it's not cancer. Then that becomes a really bad thing. Is that okay? So at the end of the day, all that we need is, okay, now in the ideal situation, let me come down here. In the ideal situation, a higher performance for all the matrices we see over here is more or less going to be good. But then I'm more particular about the level of support we have over here. That's the number of instances we use in our measurement, because that's very key. Imagine it is skewed like this, okay? This is like a quarter of, or yes, a quarter of, not a quarter per se, but then 1 out of every 5. Then definitely, if we are to go by just this scale, okay, then by the time maybe this one gets to 10, this one is 40 instances. So still, we are going to get results, but at the end of the day, it's not going to be representative enough. But of course, we may not have everything 50-50. But let's say a 45-50 in terms of the support is okay. At least it is something we can work with, because the differences is just 5, okay? And we cannot have everything accurately perfect. So at least those ones we can deal with them. And now, after looking at these support values to actually know the number of instances, now we look at the actual values we are seeing over here. Now, in terms of precision and recall, once again, the harmonic mean we see over here are things that we need to be very particular about, because the F1 score is combining precision and recall, giving us a general perspective of how good the model is. So over here, you can see that when it comes to the recall, the F1 score of the class 1, it is about 86% sure in terms of its certainty, that if I give you a prediction, I'm about 8% sure that it is going to be a good prediction. And that's simply because I've analyzed how good I am, and perhaps how incorrect or how bad I am, and put everything together to give you this final value. Now, in the case of the first class, it is giving us about a 67% assurance that whatever value I give you in terms of prediction, there is about a 33% uncertainty. And that's very huge. Okay, 33% is very huge. That's like more than, I mean, yeah, 1/3. Okay. Oh, wait, am I saying 33? Yes, 33%. Okay. That's very huge. Okay. So if you are telling me that, okay, the model is good, but for the class 1 or for the first class, predictions into that class, there's about 33% chance that it may be correct or it may be wrong. Sorry, it may be wrong in this particular instance. Then I'll begin to look at things differently based on whatever thing you are giving me. So at the end of the day, the F1 scores are combining the precision and the recall. So higher scores for these ones are the ideal things that we want to see. Now, when it comes to the, how do you call it? The macro average and the weighted average. Once again, we are also interested in the F1 scores values of those respective ones, okay? So over here, you can see that the F1 score for the weighted average just for these ones are quite high, okay? But then, of course, we are not going to keep a blind eye on the precision and the recall values we see over here. However, we can clearly see that the F1 scores are always going to be influenced by these ones. So the moment we have these ones being high enough, then that means we are rest assured that there wasn't so much problems with the precisions and the recalls. All right, please, at this point, are there any questions? Okay, so I believe the silence means no. Now, let me quickly move on to something I would want you to read. Okay, so model, yeah. So model evaluation from scikit-learn, okay? Because everything we are using over here is from scikit-learn. And these are what I would say the common ones, but then there are others that we can also look at if we have time. So I'll highly encourage you to take a look at these ones. Let's just hold on for a few seconds. And I think at this point, I can clean up everything I have over here. All right, so let's look at these ones. All right, so let me just put this in the chat so that you can have access to it right away. Okay, so it says metrics and scoring, quantifying the quality of predictions. So it gives you some things you need to read over here. And then the common cases, okay, or the predefined values of some of the things that we do is, if it is for classification, we can look at the various functions we have been dealing with. And there are some few comments that you can see over here. So for accuracy, we use the accuracy score function in there or the method in there. And for balance accuracy, and of course, you can see that there's a lot more over here. So there's one called balance accuracy. You can do further readings on this to actually know what's actually a balance accuracy. So it says a balance accuracy in binary and multi-class classification problems to deal with the imbalanced data set. Okay, it is defined as the average of recall obtained on a class. So the best value is 1 and the worst is 0. So it is saying that when you have data sets that has or shows instances of imbalance, then you are most likely, or your best bet is to look at not just accuracy, but then the balance accuracy. Because if indeed the balance accuracy is anything closer to 1 with, let's say, an imbalanced data set, then your model is doing very well. So you can look at the balance accuracy, you can look at the top K accuracy. Once again, you can just do a reading on this to get the details and also experiment. Okay. At this point, it is your job to understand what you are doing and then do further interrogations of, okay, what if I use this? What other techniques can I deploy to enhance my performance or to even get to know more of the performance that I'm looking for? Now you also have the average precision, the neck barrier score. I've never heard of this before, but then let me see what it does. Okay, it says the smaller the Brier score loss, the better. Hence, naming with loss. Okay, and it gives. I'll spend time and read this myself to actually get that information. But then these are the ones that we spoke about. For instance, the F1 score, the F1 micro, macro, the weighted, and these are this is the F1 score. Okay, but then this is the F1 macro average, and this is the weighted average. So all these ones are what we see over here with the scikit-learn, and then you can see that it goes down to the ROC curve. There's the area under the curve, and all those things we see over here. Now, in other models, we are going to do some few things over here to also do an evaluation and see. Now, you can see that Classtrain will also have its own set of how do you call it, performance metrics that we use. So over here, you can see that we are not looking at F1 score and other things over here. These ones also have their own unique ways that we can evaluate the matrices or the performance of the model. And also, you can see that with regression, we are looking at different things over here. And later on, when we get there, we are going to see. So, for instance, you are going to see some mean squared errors and all those things that you probably might have heard of in maybe in algebra and other things. Okay, so we are going to deploy them as and when it becomes necessary for our understanding. All right. Please, any questions? So what I want you to do, okay, in terms of what you need to do moving on and maybe during the vacation and other things is all the models that you built, at least you can rerun them, okay? Now, when you rerun them, try and get the classification report of each. Do an analysis of them, especially with the ones that we built with the k-nearest, the decision tree, the random forest, and all those ones, and just put them side by side, okay, on various tabs, and I'll look at each and every one. Once again, like I said, the first thing I'll look at is the support, because the support will inform me if it was fairly balanced or biased towards a particular class. Now, once I see that the support is very close to each other, then I'm beginning to look at, okay, what about the F1 score? If the F1 score is closer to 1, then I'll now begin to look at these ones. So normally my readings of these reports or classification reports is from the right to left, because these are the ones of prime importance to me. These are the ones of prime importance to me, and I go this way and stuff like that. All right. At this point, I think we are done. We've covered what we need to cover. The rest is for you to build a model and do the analysis yourself and see what values you are getting. And now, I mean, this is not done. At the end of the day, or maybe not maybe, actually later on, we are actually going to build models, and we are not going to get possibly desired outcomes of performances that we want. And then we can do hyperparameter tuning to improve the performance. Okay, part of it is some of the things we already know. Okay, trying to first of all maybe do a visualization of the data set and knowing that, okay, based on how this data set is looking, if it is for instance the support vector machine that we are using, maybe a linear separator, okay, or maybe the data points are linearly separable, so we can use the linear kernel. That's just one way of looking at it. Maybe looking at how they are intertwined, a linear kernel is not going to help us, so let's use a polynomial kernel, or let's use the radial basis function kernel. All those ones are going to help us, and then there are some few ones that we are going to learn along the line to actually improve some of these models. So we are going to build models, performances are going to be very low. We analyze the report over here this way, and then we do hyperparameter tuning to enhance the performance of those models. And hopefully, we are going to do that in the coming days, probably after the Christmas break. All right, please, at this point, any questions? Okay, so let me see. Good. So based on what we've covered so far, we've covered a lot, and at least we've concluded on everything we see over here. Okay, each and every algorithm. We've looked at the fundamental principles, some of the mathematical foundations, and how we build them. And in subsequent sessions, we are going to look at the regression. Okay, and at least we looked at how we analyze the reporting for these ones. And now after regression, we'll go back to a little bit more on deep neural networks, where we are going to train um, data set that has to do with images, okay, how we analyze images, how the computer sees images, and how it's able to do all these computations with images. And then we are going to look at, obviously, I mean, you have this outline. So we are going to see how we, beyond just building these models, how we integrate this into a web application for others to also use. And then we go to CNN, and by the time we are done, I mean, all these things are going to make sense to you one way or the other. All right, please, if there are no questions, I think we can call it a day. The video recordings will be there, so you can always go back and read, I mean, watch them, and also read some of the things I've also shared with you to get a better understanding of things. Okay, so if there are no questions, I think we can call it a day. All right, so have a good night, and we'll meet hopefully the next time.